In the vast silence between the stars, something impossible is happening. A frozen traveler, older than our sun, is bleeding water into space in a region where comets should sleep. NASA's Swift telescope caught the moment, and what it saw defies everything we know about physics, chemistry, and maybe intelligence itself. Welcome back to Vertex, where space meets mystery and science meets the unknown. Today, we explore the most active interstellar comet ever recorded, 3I Atlas, and why scientists are both amazed and alarmed. 40 kilograms of water is vanishing from an interstellar comet every single second, far from the sun in a region where even our own comets lie dormant. NASA's Swift satellite caught this comet in July 2024, blasting out steam like a miniature fire hose at 2.9 astronomical units, an activity rate never seen from a visitor between the stars. But if 3I Atlas is bleeding water so fast, why is its coma packed with strange icy fragments? And why did James Webb find carbon dioxide outpacing water by 8-1 just days later? This isn't just a comet story. It's a cosmic riddle no one has solved, and the answer could reshape what we think lurks between the stars. So what exactly is 3I Atlas hiding? NASA's Swift Observatory turned its ultraviolet eye toward 3I Atlas in late July 2024, seeking the chemical fingerprints that betray a comet's activity. The ultraviolet and optical telescope perched above Earth's atmosphere captured a distinct signal: hydroxyl radicals, flaring in the cold vacuum, a proxy for water vapor breaking apart under sunlight. Over a week of stacked exposures, the Swift team measured water loss at nearly 40 kilograms per second. This was not a trickle, but a torrent, a rate that rivals the output of a city fire hydrant, erupting from a body nearly 3 times farther from the sun than Earth. At 2.9 astronomical units, most solar system comets are silent, their ices locked away by the cold. Atlas, by contrast, was throwing water into space with abandon. The scale of this activity raised immediate questions. Calculations showed that to match the observed water production, at least 8% of the comet's surface would need to be actively sublimating, far higher than the 3 to 5% typically seen in local comets at this distance. For a nucleus estimated at 5 to 6 kilometers across, that translates to more than 7 kilometers of exposed sunlit ice. Yet, the ultraviolet emission wasn't tightly clustered around the nucleus. Instead, it spread across an extended cloud, hinting at another source. Models pointed to a swarm of icy grains, tiny fragments, each acting as a miniature steam vent. Sunlight striking these grains could vaporize water over vast distances, boosting the apparent activity far beyond what the nucleus alone could supply. Near-infrared spectra from Gemini and IRF confirmed the presence of H2O ice in the coma itself, not just at the core. The Swift team's HAZER modeling, which translates O emission into water production rates, accounted for this extended source, but the numbers still strained the limits of what standard comet physics could explain. Every measurement was scrutinized. Calibration checks, background subtraction, and sensitivity limits were debated in team discussions. But the signal persisted. The extended O, the high active fraction, and the grain-driven outgassing all converged on a single inescapable conclusion. 3I Atlas was venting water at a rate and in a manner never before observed from an interstellar visitor. The question now was not whether the activity was real, but what hidden process, deep within the coma or the nucleus, could sustain such a spectacle so far from the Sunday. August 6th brought a new layer of complexity to the puzzle of 3I Atlas. The James Webb Space Telescope, using its MI and NIR spec instruments, captured spectra that revealed a chemical signature almost unheard of among comets. Carbon dioxide is outpacing water by nearly 8 to 1. This is not a subtle difference. In most comets, water dominates. Carbon dioxide is usually a supporting player, never the star. But here, the ratio stood at 7.66 to 8 for every 1 part of water, a value that stands several standard deviations above the norm for both long-period and Jupiter family comets. The JWST team, led by planetary spectroscopists, mapped the coma in infrared light. Their data uncovered more than just numbers. Water vapor. The traditional comet driver showed up in scattered, patchy bursts, localized, uneven, almost as if it were leaking from isolated vents or erupting from icy grains. In contrast, carbon dioxide painted a broader, smoother canvas across the coma, hinting at a more uniform release mechanism. That contrast, patchy H2O, smooth carbon dioxide, suggests that the two volatiles are being liberated by fundamentally different processes, or perhaps from distinct regions within the nucleus and its surrounding debris. Other molecules joined the mix. Carbon monoxide was present, adding to the carbon profile. The team also detected a hint of carbonyl sulfide, a sulfur-bearing molecule rarely seen in such abundance. Each of these compounds carries clues about the comet's origin story. High carbon dioxide could mean formation in a carbon-rich frigid zone beyond the carbon dioxide ice line, or it could be the residue of intense radiation processing over eons between the stars. If heat from the sun can't penetrate deeply, water ice may stay locked away, while more volatile carbon dioxide escapes from shallower layers or from dust grains themselves. The JWST group scrutinized every calibration, debated detector artifacts, and referenced analogs from the solar system. But the numbers held. The dominance of carbon dioxide, the spatial contrast with water, and the presence of OCS all point to a chemistry that sets 3I Atlas apart from nearly every comet seen before. The result is a comet whose activity and composition refuse to fit a simple template. One whose chemical fingerprint is as alien as its interstellar trajectory. Avi Loeb, a Harvard astrophysicist known for his willingness to entertain the improbable, has assembled a list of anomalies that, taken together, invite a provocative question. What if the 3I Atlas is not entirely natural? Loeb points to the comet's path, threading 3 planetary approach windows in quick succession, a pattern that seems unusually well-timed for gravitational assists. He notes that perihelion, the closest approach to the Sun, happens during Earth's period of solar conjunction. For several weeks, the comet has been invisible to every major telescope on Earth, a blackout window that, in orbital mechanics, also happens to be ideal for executing an orbit maneuver, where a spacecraft fires its engines at maximum speed near the Sun to slingshot outward with maximum efficiency. Loeb argues that if the 3I Atlas were a probe or mothership, this is when it would act. The comet's sunward dust configuration, its ambiguous early measurements of brightness and size, and the timing of its solar conjunction all stack up as a cluster of oddities, individually explainable, but collectively suggestive. He calls attention to a testable prediction. If anything artificial is riding along, the most likely window for probe deployment or flyby would be between November 21st and December 5th, 2024, when the comet re-emerges from the Sun's glare and passes within observational range again. The Galileo project, a network of telescopes and sensors under Loeb's direction, is already watching for any sign of non-natural activity, accelerations, outbursts, or objects diverging from the main body. Mainstream astronomers remain skeptical, emphasizing that extraordinary claims require extraordinary evidence. So far, every measurement, water loss rates, coma structure, and chemical fingerprints fits within the boundaries of comet science. Yet, Loeb's hypothesis is not just a thought experiment, it's a falsifiable claim. If no anomalous activity is detected during the predicted window, the artificial scenario loses ground. If something truly unexpected appears, the story could change overnight. For now, the case remains open and the clock is ticking toward a decisive test. For 6 weeks, 3I Atlas passed through a corridor of invisibility, lost in the blinding glare of the Sunday perihelion, arrived on October 29th, with the comet skimming just 36 astronomical units from our star, a distance not much greater than Earth's own orbit. Yet, from every vantage point on Earth, the comet vanished. Solar conjunction had drawn a curtain across the stage, blocking the view for even the most powerful telescopes. During this blackout, astronomers on every continent faced the same dilemma. Without direct observation, prediction became guesswork. Models could simulate how sunlight might drive activity, or estimate how the nucleus might respond to the rising heat. But models are not reality. Would the comet flare into a superactive state, shed fragments, or fall silent? The answers were trapped behind a wall of solar radiation beyond the reach of optical and radio eyes alike. Global observing networks, from professional observatories to backyard astronomers, watched the clock and traded updates on every possible workaround. Some tried to catch oblique glimpses with solar coronagraphs or spacecraft positioned at odd angles. Others monitored for indirect clues, spikes in solar wind, subtle shifts in the comet's predicted path, or even rumors of detections from classified military satellites. Nothing definitive surfaced. The blackout held. With each passing day, the suspense grew. The fate of 3I Atlas depended on what happened in that hidden passage, a period when the most dramatic changes tend to unfold in comets pushed to their physical limits. Would it survive the sun's heat or fragment into a cloud of debris? The next opportunity to answer those questions would not come until late November, when the comet re-emerges from conjunction. For scientists and sky watchers alike, that reappearance is more than a routine checkpoint. It is the moment when the story resumes, and the unknown becomes visible once again. From a vantage point orbiting Mars, the European Space Agency's Trace Gas Orbiter turned its attention to 3, divided by Atlas, as the comet swept within 29 million km of the red planet. Between October 1st and 7th, the KSSI's camera snapped a series of images, capturing a coma stretching between 4,000 and 8,000 kilometers across, a diffuse envelope of gas and dust faintly illuminated by sunlight. At this distance, the nucleus itself appeared as a bright, unresolved point embedded in the heart of the expanding cloud. Careful analysis showed a single central condensation with no evidence of splitting or secondary fragments. The color data revealed a subtle blue gradient in the outer coma, consistent with sunlight scattering off small icy grains, echoing earlier ground-based hints that fragments in the coma were feeding the comet's water output. Spectral coverage was limited with no resolved gas lines, but the multispectral bands confirmed the presence of both dust and ice. In every frame, the nucleus remained compact and intact, offering a rare moment of certainty before the comet vanished behind the Sunday. For mission engineers, the campaign was a technical challenge, balancing exposure times, pointing accuracy, and data transmission across interplanetary distances. The result, independent confirmation that on the eve of perihelion, 3-2 divided by Atlas showed no signs of catastrophic breakup. Comets are fragile worlds. When they pass close to the sun, the balance between sunlight, internal ice, and structural weakness can tip dangerously. For 3I Atlas, the risk of breaking apart is not just theoretical. It's written in the history of other comets pushed to their limits. Shoemaker-Levy 9 shattered under Jupiter's tidal forces in 1992, splitting into more than 20 fragments before colliding with the giant planet. Comet 73 P. Vassman-Wachmann 3 disintegrated in a cascade of pieces as it neared the sun, its light curve flickering with each new break. Even C divided by 209, YY4. Atlas, another highly active visitor, crumbled unexpectedly near perihelion. The physical threats are well understood. As the sun heats the nucleus, thermal gradients build up between sunlit and shadowed regions. Subsurface ice turns to gas, raising internal pressure that can crack or blow out weak spots. Sometimes, outgassing is so intense that jets act like thrusters, spinning the nucleus faster and amplifying stress. Yet not every comet succumbs. If outgassing remains balanced, symmetric across the surface, it can help hold the nucleus together, venting pressure in all directions. The warning signs of fragmentation are dramatic. Sudden dips or surges in brightness, the appearance of multiple nuclei, or a spreading cloud of debris. For the 3I Atlas, these are the signals astronomers will be watching for as it rounds the sun and returns to view. Galactic modelers trace the path of 3I Atlas back through the Milky Way's thick disk, a region populated by stars nearly as old as the galaxy itself. The comet's inbound velocity, clocked between 60 and 67 kilometers per second, sets it apart from objects born in our sun's neighborhood. This is not the leisurely drift of a local wanderer, but the signature of a body ejected billions of years ago, long before Earth formed its first continents. Its orbit, just past the threshold of being bound to the sun, hints at a quiet journey through interstellar space, undisturbed by close encounters with other stars. Inside the nucleus, measured at 5 to 6 kilometers across, layers of ancient ice may have survived since the dawn of planet formation. A rotation period of 16.16 hours keeps its surface cycling through sunlight and shadow, preserving pockets of chemistry that predate our solar system. For dynamicists, these properties transform the 3I Atlas from a fleeting curiosity into a time capsule. Each molecule released into the coma carries a message from an era when the galaxy was young, offering a rare chance to study the ingredients of worlds that formed in a different corner of the cosmos. Tom Statatler, Chris Lintott, and Jason Wright approach the 3I Atlas puzzle with a discipline shaped by decades of comet science. Their stance is clear. So far, every observation falls within the boundaries of natural comet behavior. The Swift and JWST campaigns, for all their surprises, have yet to produce a single measurement that demands new physics or an artificial explanation. Thermal emission, checked across the infrared spectrum, shows nothing beyond what sunlit ice and dust would emit. The comet's path through the solar system, tracked against predictions, displays only the subtle nudges expected from outgassing, not the erratic deviations that would signal hidden engines or non-gravitational forces at work. Null results matter here. No excess heat, no unexplained acceleration, no radio or optical signals that hint at an engineered artifact. The coma's chemistry, though exotic, can be traced to formation in a carbon-rich cold environment, an outcome predicted by models of planetary system diversity. Statler and his colleagues point to the burden of proof. Extraordinary claims require evidence that cannot be explained by known processes. Until November's reappearance, every anomaly remains a challenge for cometary physics, not a breach of natural law. The bar for overturning consensus is high, and so far, the data does not clear it. As the sun swallowed 3I Atlas from Earth's view, the internet filled the void with its own spectacle. Social media feeds lit up with comet memes, speculative threads, and digital detective work. Hashtags like #AlienAtlas and #CosmicSprinkler have trended for days. Animated GIFs showed water spraying from cartoon comets, while viral posts compared the object to everything from a galactic garden hose to a stealthy interstellar probe. Some users mapped out elaborate timelines, linking every data blackout to secret maneuvers or hidden signals. Others pored over telescope logs and mission updates, convinced they could spot the first hint of artificial activity before the professionals. Discord servers and Reddit forums turned into round-the-clock rumor mills. Amateur astronomers shared blurry images and unconfirmed light curves. Each new data point sparked debates that ping-ponged between skepticism and wild hope. Conspiracy theories tangled with real science, making it hard to tell where evidence stopped and speculation began. In this noisy marketplace, every official silence became suspect, every unexplained blip a possible clue. The frenzy only grew as November approached, raising the stakes for what the next round of observations might reveal. November brings the critical test for 3 divided by Atlas. As the comet re-emerges from solar conjunction, a global network of telescopes will begin searching for any sign of renewed activity or unexpected behavior. At the heart of this campaign is ESA's JWST spacecraft, which will train its cameras and spectrometers on the comet between November 2nd and 25th. JWST's vantage point, far from Earth's interference, allows for uninterrupted monitoring as the comet climbs away from the sun's glare. The mission team has mapped out a series of targeted observations, high-resolution imaging to catch any fragments or jets, and detailed spectra to track changes in water and carbon dioxide output. Every frame, every spectrum becomes a data point in a decision tree. Does the comet brighten and expand its tail, fade into silence, or show something stranger? On the ground, professional and amateur astronomers will coordinate to reacquire the comet as soon as it clears the horizon. The Galileo project's sensors stand ready to flag any object that moves or accelerates in ways physics can't explain. Yet, patience is required. JWST's raw data won't reach scientists until February 2026, delayed by the realities of deep space transmission. The coming weeks set the stage. If the 3I Atlas survives and behaves like a comet, the natural scenario remains. If it fragments, the story shifts to cosmic destruction. But if the data reveal a true anomaly, the debate will ignite all over again. For now, the world waits, watching for the first signs that will decide the fate and the nature of our interstellar visitor. For now, the comet's origin in the Milky Way's thick disk and its unpredictable chemistry remind us that even with the best data, nature still holds the final answer. Every time we look beyond the edge of our solar system, the universe humbles us. 3I Atlas reminds us that even after centuries of discovery, we still know almost nothing about what lies between the stars. Whether it's a comet sculpted by time or something far more complex, one truth remains: the cosmos doesn't answer to our expectations. It only waits for us to catch up. Thanks for watching Vertex, your portal to space, science, and the future of humanity. If you found this story as fascinating as we did, hit that like button, subscribe, and stay curious. Because out there, the next discovery might already be on its way.